Hello everyone, my name is Yin Zhe Ma. I'm currently a professor at Stellenbosch University. So today I want to summarize about 21 centimeter cosmology, about motivation, status, and BRICS collaboration, why we can make an impact. So this basically are the photos of the telescope that here in different BRICS countries. I mean, our Meerkat telescope, the China's 500-meter fast telescope. Here I'm standing in front of a Hira telescope, the 14-meter dishes. And in the future, there will be a SKA MEAD telescope also in South Africa. So the science we are interested in is about intensity mapping of 21 centimeter, which is to measure the spin flip transition between the hyperfine level in the H1 ground state. So for the neutral hydrogen, if you have a proton and electron spin parallel, they will occupy in a higher energy state than the anti-parallel. So the transition between the two will emit a photon with wavelength 21 centimeter. So basically, we can measure this intensity map from the distant universe by using this intensity mapping technique, which really use low integration time and large angular sky coverage, and it has a lot of statistical technique to extract the target signal. So the interest period that we are interested is the cosmic dawn and reionization, and also the low redshift universe. So this is a major aim of SKA, which is a transition happened 1 billion years after the Big Bang. And this is the last process we don't know about universe. Because earlier than 380,000 years, the universe was in a hot plasma, and we can use a thermal equilibrium to describe the physics. And in fact, we are able to calculate deuterium and helium abundance with that piece of equilibrium physics. And you can calculate it in a rather precise fashion. And at late time, the galaxy has formed. And the Strong Sky Survey has mapped out a quarter of the sky out to redshift 1. And future DESI and LSST can improve it. So basically, early universe, we have already measured. The CMB has been very well measured by WMAP and Planck. Late time, yes, you only map out a quarter of the sky, but you already measure it out to redshift 1. You also know it. So only the intermediate regime of the entire universe that we don't know its much details. And that is basically the last unexploited territory in cosmology in the entire universe evolution. So here I want to give you a bit more motivation about this. For instance, this is a power spectrum of the CMB, the cosmic microwave background radiation, back to 1980s. As you can see, this was a curve by then. The expected, lambda. By then there was no lambda, but a CDM model. But then you see these error bars basically 100 times larger than the underlying signal. Now, this is the spectrum. These are the data from the Planck, from the Atacama Cosmology Telescope, from South Pole Telescope, and etc. It really gives an exquisite measurement of the angular power spectrum. So from here to here, 3 decades. 3 decades from only knowing upper limit, which is 100 times larger than the signal, to the data, to the precision that is so precise that you can measure dark energy, dark matter, and so on, the primordial fluctuation, the scale, the tilt of the spectral index, etc. In a very precise. And you can even constrain inflation model. That's crazy. The quantum fluctuation back at the early universe. So I want to show you now we are also in a similar status in 21 centimeter cosmology. So this is our Hira, the hydrogen e-power reionization array, phase 1 limit. As you can see, last year, we basically, 2 years ago, we published this upper limit. And this is a 21 centimeter power spectrum as a function of redshift. And this red arrow pointing downwards are the current upper limit from Hira, 40 dishes, 94 nights. And it's already the world competitive upper limit. And this line is the fiducial model, basically some fiducial model, and we don't know much details. And this error is also about a few hundred times larger than the underlying signal. And we are actually at a stage of pushing down this error bar and to measure the underlying fiducial model. And I hope, next 5 to 10 years, we will achieve the first detection. And that is significant. And so this is really what we are aiming to do, and that's why I'm interested in doing this collaboration. So So basically, as a summary, the status of the, I want to give a summary of the status of the low Z intensity mapping and also the high Z, the EOR study. And basically, I hope I would have enough time. So this is the low Z intensity mapping, as early as this low redshift. By 2010, Chang et al. Cross-correlated the GBT telescope with Deep 2 survey and got the first detection of this only with 2 degrees sky area. And Masui et al. Cross-correlated GBT cross-correlating with WIGO Z, and this Park telescope and cross-correlating with 2DF and also with WIGO Z and obtain the significance on each. And this is all before 2020. And then recently, after 2020, this is my postdoc basically. What he did is he stacked the central galaxies on the Park's 21 centimeter intensity map for 10 modes and 20 modes, and he can detect the accumulative halo contribution, halo emission of the 21 centimeter, which is obviously have higher emission than the beam. So he detected this cumulative 21 centimeter emission above the beam. And also, with Meerkat, we have a 200 square degree survey for this redshift range, and these are the different power spectrum at those different foreground removal level. And then we correlated the 30 foreground removal map with the WIGO Z galaxies and obtained a 7.7 sigma level detection of the cross correlation signal, which is showing here. And this is by Cunnington et al. And we are currently doing some modeling of the HODs, the halo occupation distribution, and to fit and to derive the physical parameter of what is the minimal halo that can really host a galaxy from this data. For high redshift, in South Africa, we are heavily involved in HIRA telescope, which is led by UC Berkeley, but involved with many universities in the US and South Africa, Canada, and UK. And funded by the NSF and the Gordon and Betty Moore Foundation. So this is the thing. So what HIRA measure, because it's interferometer, is visibility over here, which is a convolution of intensity with telescope beam with an exponential delay factor. So this can be understood as the converting the energy into time delay of the signal, a bit like the Heisenberg uncertainty principle. You have the energy uncertainty and time uncertainty multiplied together greater than h bar. And this is really utilize the Heisenberg uncertainty principle, basically, to convert that into the time delay of the signal, which would correspond to different Fourier modes on the sky. So in total, HIRA is 350 dishes. I think, yeah, so altogether. And in the Karoo Desert of South Africa, each of these 14-meter dish, and covering this redshift range, 4.7 to 27, which is a frequency range of 50 to 250 megahertz, which exactly cover the redshift range where the universe transits from neutral to ionized. So here is the location, and basically, if you zoom into the Northern Cape, Karoo Desert, you will see our dish layout, basically, dish layout for HIRA. And because the location, it also does the drift scan for declination of minus 30 degrees with a width of about 5 degrees north and south. In the far future, we hope to map the entire universe using the intensity mapping, which will consist of a legacy survey of the 21 centimeter volume of the universe. So far for HIRA, we can only maximally map out 1,400 square degrees, not the full volume yet. And because of the interferometer structure, we unfold the Fourier modes on the sky to modes that are parallel and anti-parallel, parallel and perpendicular to the line of sight. The observed regime is called a window. And the left and right parts are set by the angular extension of the field of view. So this is the angular extent of the field of view, and this is angular resolution, which tells the finest mode you can measure perpendicular to the line of sight. And likewise, the low K parallel mode is set by the foreground, the intrinsic foreground, dominated by very smooth synchronous emissions. And top cut is a frequency resolution for the K parallel. So therefore, the four edges of the Fourier space are bounded by different experimental specifications. Finally, there's another important effect called wedges. foreground wedge, which really tells how the interferometer is being designed. So these are a little bit too much details. Let me jump into the current upper limit. So this is our first power spectrum at redshift 7.9. And we place upper limit on the power spectrum. We can say at this redshift, the power spectrum cannot be larger than 457 millikelvin squared. So we can place the worked competitive upper limit on this power spectrum plot with only 94 nights data from 40 dishes of Hera. Very conservative EOR window, using very conservative EOR window modes. So what does this indicate? First, we can say the IGM was heated above the adiabatic limit at redshift 7.9 at greater than 95% confidence level. That is to say, if nothing happened to the intergalactic medium from the recombination all the way to redshift 7.9, then IGM is just adiabatic cooling, but this is not the case. Because if the spin temperature is very low, then this will be a very big negative thing. And when you square it, when you do the power spectrum, it will be very positive. However, we put an upper limit on that, so that will set the limit on the spin temperature. So we can rule out the coldest spin temperature during the reionization. So how do you compare this result with edges, the famous single dish measurement in Australia? So here, I basically convert this plot into TS over T radial, and this different data with upward error bar is from Hera, whereas edges is showing over here. So at redshift 8 to 9, the IGM, the intergalactic medium, is definitely heated above the adiabatic cooling limit. Then it's possible to cool the intergalactic medium by this 0.5% of the immediately charged dark matter, which is advertised by edge experiment, but then heated up later, due to some other mechanism. Certainly, the adiabatic cooling of the intergalactic medium is ruled out, but this mechanism is certainly currently allowed. And in the future, if Hera is going to place more data at higher redshift, then it can really confront the edges result, the single dish measurement, hopefully in the current phase of Hera. So our long-term goal is to achieve the first detection of the 21 centimeter power spectrum and to be able to pin down the reionization history. This is the current constraints on the hydrogen neutral fraction by the CMB, by the measurement of the optical depths, and a few galaxy mocks, galaxy works. We hope to have a clear picture of how this curve, hydrogen neutral fraction really evolved from 1 to 0. And also we can hopefully to constrain, for instance, the optical depth and also the primordial fluctuation amplitude, AS, by a precise fraction. And this is currently also highly constrained by the CMB, but hopefully we can also do that in 21 centimeter. And also about neutrino mass, which will have a lot of interest to do, and therefore knowing how the neutrino mass hierarchy arrange, and therefore knowing which scenario of the neutrino oscillation is correct, and so on. So basically, I want to show that in BRICS country, we do have many 21 centimeter telescope going on. Like South Africa, we have Meerkat, Hera, and SKA. And in Brazil, there is a Bingo telescope. In India, there's a GMRT. And in China, there is a FAST telescope, and so on. So there's a lot of overlapping interest in between, a lot of technique that people can develop and to share technique and share some thought on, do some collaborations. And this is one of the meetings that I organized many years ago in 2018 in Durban. And you can see there's a lot of delegates from these 5 different countries and come and visit. I think Takalani was also there by then. So it was a nice meeting in Sri Lanka. So in summary, the 21 centimeter cosmology is a very promising field and is absolutely a new, perhaps last window in cosmology. So cosmology is not like other fields of astronomy. Once it's done, it's done. For instance, for microwave background experiment, if you launch another satellite, you should see the same data set as the CMB. Right? If you don't see the same, then of course, apart from different systematics, etc., the real value may be different, but you should see the same thing. Once it's done, it's done. So that's why I'm so fascinated by 21 centimeter, the EOR, because it's really the last territory in cosmology, right? And In the next few years, the low Z intensity mapping will increase by sky coverage and redshift, and therefore mapping out the lossy structure in a novel way. And many cross-correlation work can be done to understand the structure formation, testing gravity, and constraint cosmology. And the high Z EOR data is still heavily contaminated by the foreground and potential calibration issue we hope to measure the first slide in the next 5 years. And I think the BRICS countries have a unique advantage and synergies on 21 centimeter cosmology. Thank you.